We're going to be differentiating a logarithm of x with a base of a. One thing you need to realize is that that a value is a constant. It's the base of a logarithm. It can be any number. Just know that it's a constant. It'll help us here in just a minute. Something else that we're going to assume when I show you how we can differentiate this is that we know that the log of x base a is equal to, using a change of base formula, the natural log of x divided by the natural log of a. That will come into play here in just a second. So I'm going to rewrite this logarithm with our change of base formula. So it's still going to be the derivative with respect to x of the natural log of x over the natural log of a. Then I can break this fraction up using multiplication. So that's the same as the derivative with respect to x of 1 over the natural log of a, which is a constant. The natural log of a is a number, 1 over that is still just a number, multiplied by the natural log of x. Now, like we talked about, if 1 over the natural log of a is a constant, I can take that outside of our derivative. So it's the derivative with respect to x. So it is 1 over the natural log of a multiplied by the derivative with respect to x of the natural log of x. Now, based on our previous knowledge, we know the derivative of the natural log of x. That derivative is 1 over x. So this is 1 over the natural log of a multiplied by 1 over x. This will be our derivative of the log function. Simplifying, it is 1 over x natural log of a. For our next example, we're going to find the derivative of an exponential function where a is the base and a is a constant. So it's an exponential function because we have a variable as an exponent. Now, I'm giving you the actual formula here. It's a to the x natural log of a. We'll prove that formula in class, but for now, let's just go ahead and use this fact that the derivative with respect to x is a to the x natural log of a. So doing so, our example that we're going to differentiate is 10 to the x squared. Now that looks like we have a function inside of a function. So we're going to use the chain rule here, and I'll show you all the steps using substitution so that we can see where the chain rule is going. So if I let u equal x squared. Now the chain rule tells us that the derivative with respect to x is equal to the derivative with respect to u multiplied by the derivative of u with respect to x. This is the chain rule in Leibniz notation. Alright, so using our u substitution, if u is equal to x squared, the derivative with respect to x is the derivative with respect to u, so this is 10 to the u. So the derivative with respect to u is simply 10 to the u natural log of the base, which is 10. And we're going to simply multiply that by the derivative of u with respect to x. Well, u is x squared, so the derivative of that is 2x. Plugging back in our u. This is 10 to the x squared natural log of 10 multiplied by 2x. Moving that around a little bit, if you would like, we can simplify and bring the 2 to the front. It would be 2x multiplied by 10x squared multiplied by the natural log of 10. This is a constant. It's a number. We have 10 as the base of an exponential function, and we have 2x. All of those things are multiplied together. For the next example, we're going to use the theorem for the antiderivative of a to the x dx. Using the previous example and the previous theorem, you probably can see where this comes from. If I have a to the x dx and I want the antiderivative, Well, the derivative was a to the x multiplied by the natural log of a. So if I want to undo that, it's probably a to the x divided by the natural log of a, and obviously we have plus c because it's a family of functions. So let's go ahead and apply that to find the definite integral from 0 to 5 of 2 to the x dx, or the area under the curve from 0 to 5 of 2 to the x. Using this, we need the antiderivative, which is 2 to the x over the natural log of 2. And that will be evaluated from 0 to 5. Now all we need to do is simply plug those values in and we'll have our number using the fundamental theorem of calculus. So it would be 2 to the 5th over the natural log of 2 minus 2 to the 0 over the natural log of 2. Simplifying to come up with our value, it is 2 to the 5th minus 2 to the 0 is 1 over the natural log of 2. 2 to the 5th is 32 minus 1 is 31 over the natural log of 2. And obviously if it was a calculator active problem, you could type that in and round or truncate to 3 decimal places. For our next example, we're going to actually use logarithmic differentiation to find the derivative of y. The function y is a very complex function and would be difficult to differentiate because we have to use quotient rule and product rule along with the chain rule. Basically, it's going to end up being a disaster. But we can use a little trick in order to make this problem a little easier. In order to do so, I can take the log or the natural log of both sides of the equation. Just like I could add 5 to each side. As long as we do the same thing on each side, the equation will stay balanced. So I'm going to take the natural log of both sides. Okay, natural log of both sides. Now, this helps us because you know how to expand natural logarithms to make this an easier process. You know, if it's multiplication, we can expand it using addition. If it's division, you can expand it using subtraction. So this, and I'm going to just simplify here, the natural log of y is equal to the natural log of x to the 3/4 plus the natural log of the square root of x squared plus 1 minus the natural log of 3x plus 2 to the 5th power. This makes our problem a little bit easier, especially since we know how to differentiate a natural log function now. We will end up differentiating with respect to y, and we will use implicit differentiation. So that'll be a good review as well, but I'm going to simplify this side just a little further. So it's the natural log of y is equal to 3/4 the natural log of x plus 1/2 the natural log of x squared plus 1 minus 5 natural log of 3x plus 2. Once we have it this far, we'll go ahead and use implicit differentiation to differentiate. So that will give us the derivative of the natural log of y is 1 over y multiplied by the derivative of y with respect to x. That's implicit differentiation with respect to x. Here, the natural log of x has a derivative of 1 over x multiplied by 3/4 plus 1/2 multiplied by the derivative of the natural log of x squared plus 1. And you may remember a little shortcut, it would be the derivative of the inside over the inside. Minus 5 multiplied by the derivative of the inside, 3 over 3x plus 2. This will be our derivative. Now we'll simplify and then we'll end up having to solve for the derivative of y. So I'm going to simplify this side just a little bit first. So it's 1 over y dy dx is equal to 3 over 4x plus The 2's are going to cancel, and it would be 1x over x squared plus 1 minus 15 over 3x plus 2. We have it in almost our final form. We're trying to solve for the derivative of y with respect to x. That's what we're looking for. We're looking for the derivative of y with respect to x. So, simplifying. I need to get rid of this 1 over y. Now, we have a y and an x. I want the derivative of y with respect to x. So we're going to have to do something a little tricky here. And you may remember from our implicit differentiation, we know that y is equal to this. So we will plug that back in for y. So I'm going to divide both sides by 1 over y, which is the same as multiplying both sides by y. So our derivative of y with respect to x, multiply both sides by y to cancel out 1 over y, this is y. So it would be x to the 3/4 square root of x squared plus 1 over 3x plus 2 to the 5th multiplied by whatever I had on this side, which is 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. This is our derivative of y with respect to x using logarithmic differentiation. For the last example for our differentiation, we're going to go ahead and use logarithmic differentiation again. So doing so, I'm going to take the natural log of both sides. This helps us because I have some sort of function as an exponent, but my base is also a function. So it will help us because now I'll be able to take, using our logarithm properties, I can take this exponent and bring it out front. So doing so, I'd have the natural log of y is equal to the square root of x multiplied by the natural log of x. Now, differentiating with respect to x, we're going to differentiate using implicit differentiation. So, applying that, the natural log of y is 1 over y, the derivative of y with respect to x, chain rule, implicit differentiation, equals, so I'm differentiating both sides here, product rule. So it would be the first multiplied by the derivative of the second, plus the second multiplied by the derivative of the first. This is x to the 1/2. So that will be 1/2 x to the negative 1/2. That is product rule. I'm going to simplify this side just a little bit. So it will be 1 over y dy dx is equal to the square root of x over x plus, simplifying this, well, I know this part is 1 over 2 square root of x. So it would be the natural log of x over 2 square root of x. This is what we have up to this point. Now, simplifying. X is x to the 1, or square root of x is x to the 1/2 power. If you want to simplify that just a little bit, we can. So I would subtract exponents. 1/2 minus 1 is negative 1/2. So we could go ahead and use that. So it's 1 over y dy dx is equal to, and like I said, it would be 1 over the square root of x plus natural log of x to square root of x. We can simplify this if we want to get a common denominator. You don't necessarily have to simplify. Remember, what we're trying to find is the derivative of y with respect to x. If I do simplify this, I would multiply this fraction by 2 on the numerator and denominator, and then I would have a common fraction so that I could add them. Adding them would give us 1 over y dy dx is equal to 2 plus the natural log of x over 2 square root of x. So that's just simplifying, getting a common denominator. I'm solving for the derivative of y with respect to x. Well, it's 1 over y here, but I want it in terms of x. Remember, y is x to the square root of x. So if I have to simplify this or solve for dy dx, I multiply both sides by the reciprocal or multiply both sides by y. So this is the derivative of y with respect to x is equal to x square root of x multiplied by what I had, 2 plus the natural log of x over 2 square root of x. And that right there would be our derivative of y.